Good day. We will be doing today our heat transfer basic problem solving in this video. So hop on and enjoy learning. In this design problem, we have an ice skating rink is located in the second floor of an indoor shopping mall with an environmental air temperature of 22 degrees Celsius and the radiation surrounding walls of about having a temperature of 25 degrees Celsius. Now, the convection heat transfer coefficient between the ice and air is 11 watts per meter square degrees Celsius because of the air movements of the skaters. The emissivity of the ice is 0.094. The temperature, environmental air temperature of the first floor is about 25 degrees Celsius with a convection heat transfer coefficient within concrete floor which is equals to 10 watts per meter squared per degree Celsius, and the thickness of the concrete floor is 5 inches, having a thermal conductivity of 2.32 watts per meters per degree Celsius. So the problem here is that how long does it take to melt 2 inches of ice if no cooling is supplied? So we have assumptions. The first assumption is the ice temperature is equals to 0 degrees Celsius. Also, the size of the uh, ice skating rink is about 12 by 25 meter. And we also have a negligible contact resistance between the ice and the concrete floor. Aside from that, the latent heat of fusion of ice is equals to 334 kilojoules per kilogram, or it takes about 334 kilojoules to form a 1 kilogram of ice, or vice versa, it takes about 334 kilojoules to get inside a 1 kilogram of ice to make it and change it into water phase. So we have to label the values. First, we have at the first floor, the temperature of environment at the first floor is about 25 degrees Celsius. Also, the convection heat transfer coefficient is 10 watts per meter squared degrees Celsius. Also, we have the K of the floor, which is, or the thermal conductivity of the floor is equals to 2.32. That is in watts per meter per degree Celsius, and the thickness we have delta X is equal to 5 inches. And if we convert that into meter, so we have 0.127 meter. So what else? Okay. So we have in the second floor, we have the temperature of the environment in the second floor is about 22 degrees Celsius. The temperature of the wall is 25 degrees Celsius. Also, we came here with the temperature of the ice is equals to 0 degrees Celsius. The emissivity is 0.94. The convection heat transfer coefficient of the second floor is 11 watts per meter squared per degree Celsius. And of course, the area, which applies to both second floor and first floor, we have 12 meters by 25 meters. So this becomes 300 meters squared. Okay, what else? So is that? So what really involves here is in the first floor, we have a convection and conduction heat transfer. In the second floor, where the ice skating rink skating rink is located, we have a combination of radiation and convection. So the involved heat transfer total in this problem is we have to establish the equation Q radiation plus Q convection plus Q, since this is a combination of conduction convection, so we have just to put simply this as CC. Okay, so first we have to analyze and compute the QCC. So we have a change of, or the difference of temperature from 25. Okay, so this is 25. Okay, I think we have to establish first the equation so that you can manage to follow. So we have T alpha, environmental temperature of the first floor minus the temperature of the ice, okay, multiplied by the area. We have all over 1 over H convection heat transfer coefficient plus delta X, or the thickness of the floor, over its thermal conductivity K. So we have a series of resistance here in this equation. So those, by substituting, we have here 25 degrees Celsius minus 0 degrees Celsius multiplied by area, which is 300 meters squared, and all over 1 over 10 watts per meter squared degrees Celsius plus, okay, we have to make it in meters now. So we have 0.127 meters of delta X. So we have 2.32 watts per meter per degree Celsius. Okay, so now what happens is that this one, by dimensional analysis, this becomes meter squared, and this one goes up, so becomes meter squared. So again, the meter squared will be cancelled, and the watts, which is shown here, will go up. So this becomes watts, and also the temperature, which is degrees Celsius, is also cancelled. So by dimensional analysis, we have, substituting the value, we have 48,467 0.97 watts or 48.467 kilowatts. Okay, so again, we have also the Q radiation is given by area multiplied by the Stefan Boltzmann constant and the emissivity. All are multiplied to the difference of wall temperature into the fourth power minus the ice temperature, okay, to the fourth power, and through substituting, okay, we will have 300 meters squared multiplied by 5.68 times 10 to the power of negative 8, which has a unit of watts per meter squared per Kelvin. And again, we multiply this one by emissivity of 0.94 and to be multiplied by 25 plus 273.15 to the power of 4 minus, so this one will be in Kelvin. This one is 0 plus 273.15, this to the power of 4, and this one also is in Kelvin. I mean, the Stefan Boltzmann has the k to the fourth power. So those, we have to cancel the Kelvin to the power of 4, also the meter squared. So Q radiation is just equal to 37,341 watts or 37 point, sorry for that, 37.341 kilowatts. So another one is the Q convection at the second floor, which is equals to heat transfer convection coefficient at the second floor multiplied by the area and multiplied by the difference of environmental temperature in the second floor minus the temperature of the ice. So by substituting, we have 11 watts per meter squared per degree Celsius multiplied by 300 meters squared multiplied by the difference, which is 22 degrees Celsius minus 0 degrees Celsius. So we have to cancel out the degrees Celsius, also the area, meter squared. So we are given 72,600 watts or 72.6 kilowatts. Those, we have a total of uh, adding all to the equation given earlier, we have Q total is equals to 158.408 kilowatts. Now, also, the volume of the ice that is to be melted is just equal to the area times the x, or the melt, or the height of the melt. Now, going from previous equation, from previous values, we have 300 meters squared of area multiplied by, when we convert this 2 inches into meters, so we have 0.0508 meters, and the volume is just equals to 15.24 meter cube. Now, we also have the density of the ice. Remember, the density of the ice is less compared to the water. That's why the ice, although it's at solid state, it floats in the water. So the density of the ice is 917 kilograms per meter cube. The mass that are to be melted is equal to volume times the density. So we multiply this one, 15.24 meter cube multiplied by 917 kilograms per meter cube. We have the omission of the meter cube. So the ice to be melted is 13,975 kilograms. Okay. Therefore, the heat, or the latent heat of fusion involved in a 13,975 kilograms will be equal to latent heat of fusion of the ice multiplied by the mass. And therefore, we have 334 kilojoules per kilogram multiplied to the mass, which is 13,975 kilograms. So we have to conceal the kilograms. So therefore, Q melt is just equal to 4,667,676.72 kilojoules. Now remember, the Q total is the heat transfer rate. So when we transform that into kilojoules per second, this would give us time through dimensional analysis. Time, therefore, is the Q melt over the heat transfer total rate, which is just equal to 4,667,676.72 kilojoules divided by the total heat transfer rate, 158.408 kilojoules per second, and therefore the kilojoules cancels, the second goes up, therefore the time is 29,466 seconds. Or if we transform that into hours, we have 8.19 hours. Okay, so this is our final answer.